So a reversible reaction is one that can proceed in both the forward and the reverse directions. And until recently, we're mostly looking at just reactions going in the forward direction. But there are many reactions that can go in both directions. So this is one of them. The hydrogen and the iodine molecules can react with each other and form two molecules of hydrogen iodide, or these two hydrogen iodide molecules can bump into each other and decide that they'd rather be individual hydrogen and iodine molecules again. And the reaction proceeds in the forward direction and in the reverse direction. When we get to dynamic equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. Both of those reactions are still happening. The forward reaction is happening, the reverse reaction is happening, but because they're happening at the same rate, the overall concentrations of reactants and products isn't changing. And if you're just looking at concentrations of products and reactants, it doesn't look like anything's happening, but it actually is happening. The reactants are being depleted at the same rate as which they are formed from the reverse reaction. The products are being depleted at the same rate as they're being formed by the forward reaction. Does that make sense? It's kind of an odd concept. I'm getting a lot of blank stares. I think that probably didn't make sense. We're going to go ahead anyway. And hopefully, when we talk about it some more, maybe it'll make some sense. At least that's what we can hope for. Okay. So again, we're still looking at this high reaction, very friendly reaction here. It's reversible. So if we start out at time 0 with only reactant molecules, here we've got 8 molecules of hydrogen, 8 molecules of iodine, 0 molecules of high, the product. The reaction can only proceed in the forward direction because there's no high molecules to interact with each other. As this goes forward, some of the reactant molecules, the hydrogen and the iodine, are going to react and they're going to form the product molecules HI. Now, these HI molecules can react in the reverse direction and reform hydrogen and iodine. The rate of that reverse reaction is going to increase as the concentration of HI increases. So we go on to 30 seconds, and now we've got 4 molecules of H, 4 of I2, and 8 of HI. And at this point, if we've reached dynamic equilibrium, we can let the timer go. We can watch this reaction for a very, very long time, and the amounts of reactant and product are not going to change. It's still going to be 4, 4, and 8. It's not going to change. But these guys are busy. They are making relationships and breaking up with each other. It's just going back and forth and back and forth. Any glimmers of understanding? I got a couple nods, so that's encouraging. What is important to understand is that being at equilibrium does not mean that the concentrations of reactants and products are equal. It's not that it's 50-50, half and half. Okay? Exactly where that equilibrium lies depends on a bunch of other factors. But it's not just in the middle. So we have this analogy where two different fantasy worlds meet. We've got Narnia and we've got Middle Earth, and they're separated by a river. So we're going to look at population changes as an analogy for equilibrium. So initially on this map, we have a lot of people living in Narnia. There's very few people living in Middle Earth. When conditions are crowded, people are competing for resources, and they just want some space, right? We can understand why some of these people would look across the river and say, oh, there's all this land over there. I'm going to move across the river to Middle Earth because it's more attractive to me. So initially, all of the movement is from Narnia to Middle-earth. There's nobody over here initially to move back to Narnia. So there can't be anybody moving into Narnia because there's nobody over there. As we get more and more people moving to Middle-earth and the populations get a little more even, not necessarily exactly even, but we get some people over here. Now some of these people decide that they think Narnia looks better and they wish they hadn't come over here, so they're going to go back, right? Does that make sense? Now if Middle-earth is a really great place, the climate's awesome, the ground is fertile, all these natural resources, much nicer than Narnia, then you're going to have more people in Middle-earth than in Narnia. If the opposite is true, and Narnia is a nicer place to live, the population here will be larger. People will still be here because there's trade-offs, right? It's like my husband and I lived in the Bay Area for 3 years. I mean, there's some really awesome things about the Bay Area. The weather is incredible. There's all these things you can do. The ocean and just all kinds of stuff. But it's crazy expensive. You can't afford to do anything when you live there. You know, and there's just people everywhere, and you're in line. You know, you're looking for parking places at the grocery store, and you're standing in lines, and it's kind of maddening. So we moved to Reedley, where the climate kind of sucks. But I go to the grocery store, and I don't have to search for a parking spot. There's lots of parking places, right? And so there's advantages to living in a less populated area, even though maybe it's not as attractive to people as a whole. So we can understand, I think, how the population here is not going to have the same number of people in Narnia as in Middle-earth. There's going to be some on both sides, but the relative numbers depend on some other factors, right? So in a dynamic equilibrium, we do not have the same number of molecules or reactants and products on each side. What we do have is an equal number of people moving to Middle-earth and the same number of people moving from Middle-earth to Narnia. Because as this gets more crowded, then the rate of emigration to Middle-earth increases. It has to do with the crowding. That's the concentration of the reactants. If the concentration is higher, the forward reaction goes faster. But as the concentration decreases, then the reaction rate decreases. And so it's going to regulate itself. Any questions? And we're going to watch a movie.
Say two people are walking down the street and they bump into each other. They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if two people were to bump into each other, and during that collision, one person's arm got severed and reattached to the other person's face? Now that sounds really weird, but it's similar to one of the many ways that molecules can react with each other. Two molecules can join and become one. One can split apart and become two. Molecules can switch parts. All these changes are chemical reactions, and we can see them happening around us. For example, when fireworks explode, or iron rusts, or milk goes bad, or people are born, grow old, die, and then decompose. But chemical reactions don't just happen willy-nilly. Everything has to be right. First, the molecules have to hit each other in the right orientation. And second, they have to hit each other hard enough, in other words, with enough energy. Now you're probably thinking that a reaction just happens in one direction and that's it. Sometimes that's true. For example, things can't unburn or unexplode. But most reactions can happen in both directions, forward and reverse. There's no reason that our face arm guy can't bump into armless girl, reattaching that arm back to its original socket. Now let's zoom out a bit. Now let's say that you've got 1,000 people on the street. and all of them start with their limbs normally attached. At the beginning, every collision is a chance for person A to transfer an arm to person B's face. And so at the beginning, more and more people end up with arms attached to their faces or arms missing. But as the number of people with arm faces and missing arms grows, collisions between those people become more likely. And when they bump into each other, guess what? Normal appendage people are reproduced. Now the number of limb transfers per second forward will start high and then fall. And the number of limb transfers per second backward will start at 0 and then rise. Eventually they'll meet, they'll be the same. And when that happens, the number of people in each state stops changing, even though people are still bumping into each other and exchanging limbs. Now, how many people do you think there are in each state? Half and half, right? No. Well, maybe. It depends. It could be 50-50, but it could be 60-40 or 15-85 or anything. We chemists have to get our little gloved hands dirty. Well, we're in a lab, so not really dirty, to figure out what the actual distribution of molecules is. Even though each of these limb transfers is a pretty dramatic event for the people involved, if we zoom out, we see population numbers that don't change. We call this nirvana equilibrium, and it doesn't just happen with chemical reactions. Things like gene pools and highway traffic show the same pattern. It looks pretty still from 30,000 feet, but there is lots of crazy stuff happening on the ground. You just need to zoom in to see it.
Okay, does it make a little more sense now? Yeah, I love that video.